going to have the x plus y. Now, where's my red? X plus y, right? So before I keep going, x is a real number, y is a real number, and both of them are positive, by the way. X plus y is equal to x times y. Okay. X plus y is equal to x times y. And scalar multiplication, we have k times, do I have x, I think? K times x. K times x is equal to x raised to the power k. Now k is any scalar. Any scalar. So k can be positive, negative, or 0. But x itself is only a positive number, right? So scalar multiplication, it could be any real number. Any real number I want it to be, any scalar. X is only the positive real numbers, okay? All right, so I want to make sure you guys got that and it's clear that that's the case. Okay, all right. So some examples, let's look at how this would work. Let's do an example. Let's say u is equal to, let's say 4, and v is equal to, I don't know, 2. And I want to do u plus v. Oh, let's get a k. K equal to 3. Okay. Okay. So let's do u plus v. Okay. That's the same thing as 4 plus 2. What is 4 plus 2? Well, 4 plus 2 is going to be the same thing as 4 times 2, which is 8. So 4 plus 2 is 8. Okay. What about k times v? Let's do k times v. So I have 3 times v. That's my k. Let me do k times v. Which is the same thing as 3 times, what was it, v is 2. Okay. What is 3 times 2? Well, that's the same thing as 2 to the 3rd power, which is 8. So 3 times 2 is 8, and 4 plus 2 is 8. Okay? Right. Makes sense to me. Right? Hopefully it makes sense to you too. Now that we kind of have an idea of how that works, right? What is going to be, let's suppose I want to know what is negative u. Well, no, actually, what's the 0 vector here? What's the 0 vector? So essentially the 0 vector is going to be something, so when I add a number plus the 0 vector, I get the number back. The number plus the 0 vector, I get the number back. And when you look at this, you can probably guess what it has to be, right? The 0 vector has to be 1. The 0 vector has to be 1. And I'm going to show you guys a really neat way to figure out what the 0 vector is if you know that something is a vector space. The 0 vector is 1 because suppose I take u plus the 0 vector. So if I do 4 plus 1, right? I get 4 times 1, which is 4. So 4 plus 0, right, is 4 plus the 0 vector is 4. 4 plus the 0 vector is 4. 4 plus the 0 vector is 4. Okay. Now there's kind of a neat way to be able to figure out what the 0 vector is if you know that something is a vector space. Remember, I had those properties that we put down. If something is a vector space, then I can say the 0 times the 0 scalar times the vector is going to be 0 times any vector is going to be the 0 vector. Okay. I had a hard time saying that for some reason. So for instance, if I want to find a 0 vector, right, I could do 0 times u. 0 times u. What was u again? Well, u was 4, right? 0 times 4. I could have chosen any positive number. I'm just using u in this case, being 4. Okay. If we go by our scalar multiplication, this is the same thing as 4 to the 0 power. 4 to the 0 power is 1. So I guess I can use this property that the 0 vector is equal to 0, the number 0, times a vector in my set. Okay. In this case, I get 1. So I know that my 0 vector has to be 1. What about negative u? Let's talk about negative u. Let's do negative v. I've done u enough. Let's find negative v. Okay, remember that v is 2, right? What we want to get is that when I add v and negative v together, I want to get the 0 vector back. Essentially, when I add v and negative v, I want to get 1. Okay. When I add v and negative v, I want to get 1. When I add v and negative v, I get 1. So using the addition that we've set up, what is the positive number, right? Because we have to make sure that my numbers are positive, that I can add to 2 and get 1. Okay? What's the positive number that I can add to 2 and get 1? And if you guys have realized it, it has to be what? 1/2, right? Negative v is 1/2. How does that work? Well, let's do v plus negative v. So v is 2 plus negative v, 1/2. 2 plus 1/2 is 2 times 1/2, right? Which is equal to what? My 0 vector. Ta-da, right? Astounding. Is there an easier way to figure out negative v? And there is, right? If v is if you have a vector space that you're in, then I can figure out what negative v is too, right? Negative v can be found by doing this. Negative v is the same thing as negative 1 times v. Scalar multiplication. Negative v is the same thing as negative 1 times v. Negative 1 times v. V was 2, right? So I have negative 1 times 2. What's negative 1 times 2? Well, negative 1 times 2 is 2 to the negative 1, right? What's 2 to the negative 1? 1/2. Notice that 1/2 is a positive number, right? So 1/2 is in that set. Negative 1/2 is not in that set. Negative 2 is not in that set, right? 1/2 is in the set that we've set up, right? And it follows the addition and the scalar multiplication that we have applied. Not only that, but if I wanted to, I could go to every single one of these 10 axioms and they will all be true. When I add 2 positive numbers together using this addition, I get a positive number. If I multiply a scalar, any scalar I want, times a positive number using this scalar multiplication, I get a positive number back, right? It doesn't matter in which order I add these numbers together using my addition. It doesn't matter if I have another vector that I want to add to that. If I have another positive number I want to add to it, I'm using this addition, I'm still going to end up with a positive number, and they're going to be exactly the same number, okay? We already saw the 0 vector. We already seen the negative u, right? We saw the additive inverse is essentially what this is called. the additive inverse. We've seen, and then you can go through and you can also prove these rules as well. I'm not going to do that just for the sake of time, but they are easy and fun to prove, and you should try it out at home. One more. One more if I can find it. All right, here it is, here it is, here it is. Very good, very good. The last one. Let V, hopefully you're finding this interesting. I kind of like this myself. This is fun to me. It's a pretty interesting, neat section. Let V equal R. And let's define. So what do I mean by that? So V is a vector space, which is the real numbers. So it's not just all positive real numbers, just any real number. So this V is going to be a set of all real numbers with addition and my addition is that x plus y is equal to x plus y plus z. Okay, let me put a, okay, red number between. So with addition, x plus y, so x plus y, right? So when I add these guys together, the result is going to be the addition of x and y, just like we normally have it, but then I'm going to tack on a plus 7. And scalar multiplication. I have that C, or K, it doesn't really matter what you call it, C times X is equal to CX plus 7 times that C minus 1, I think is what I have here. And let me put my multiplication sign here. So essentially, scalar multiplication of C times X is going to be equal to C times X, so a regular multiplication, plus 7 times C minus 1. Okay. So only thing I have to make sure is that I get a real number back. So this is a lot easier than this one here. I have to make sure I get positive numbers back. Let's do a quick addition. Let's see what's a good one. 1 plus 5. Oh, I need to use a different. 1 plus 5. Okay. So I'm going to add 1 and 5 together. What should I end up with when I add 1 and 5? Well, going by my addition, I get 1 plus 5 plus 7, which is, what's that, 13? So 1 plus 5 is 13. I don't need this 1 here. What's that doing there? Okay, so here I'm assuming my U is equal to 1, my V is equal to 5. Let's say our C is equal to, let's say, well, let's just make something up. Let's do another one. So that's scalar, that's addition. Let's do multiplication. So I can do 3 times 2. 3 times 2. Okay. 3 times 2. So I'm doing scalar multiplication. So this is my C. Okay, this is my C. What I'm using here. So let's work it out using this scalar multiplication. I get 3 times 2 plus 7 times 3 minus 1. Did I do that right? I think so. I think so. 3 times 2 plus 7 times 3 minus 1. What do I get when I do that? I get 6 plus, here I have 7 times 2. 6 plus 7 times 2, and that gives me 14, 20. When I do that. Okay. So yeah, so 3 times 2, yeah, plus 7 times 3 minus 1. Yeah, this is my thing. Now the interesting thing is, what happens if I were to rearrange the order? So let's suppose I do 2 times 3. Okay, 2 times 3. So now this becomes my C. This becomes my C. So 2 is my scalar now, and 3 is my vector. Here 3 was my scalar, and 2 was my vector. So now I'll rearrange them. So 1 is the vector, 1 is the scalar. If we do this one now, we get 2 times 3 plus 7 times 2 minus 1. So we get 6 plus 7, which is 13. Right. So we have to be careful here, right? When we're doing this, the order, because 1 is a scalar and 1 is a vector, right? We don't get the same answer, right? Which makes sense. 1 is a vector, 1 is a scalar. So even though they look similar, they're not the same. 1 is a scalar, 1 is a vector. And so you've just changed which one is which. So it seems like the math is broken, but that's not the case. We're dealing with 2 different mathematical objects. Here we're dealing with the mathematical vector 2. Here and the scalar 3. Here we're dealing with the mathematical vector 3 and the scalar 2. So they don't have to be equal to each other. If we were dealing with both of them being vectors or scalars, then it's possible that we would get the same thing. But that's not what's happening here. All right. What is the 0 vector? What is the 0 vector? Well, I already told you that this is a vector space. So since this is a vector space, I can do 0 times u, right? And I just picked the u that I have over there, 0 times u. So I chose u to be equal to 1. 0 times 1. Plugging in, right? 0 times 1 I get 0 times 1 plus 7 times 0 minus 1. So my 0 vector, if I did it correctly, is that negative 7? What I have here? Let's see if that works out. Let's do some addition. Let's do 5 plus negative 7. 5 plus negative 7. If we do 5 plus negative 7, we get 5 plus negative 7 plus 7, right? Going by that addition that we have there, which gives us 5. So essentially 5 plus the 0 vector, right? Because negative 7 is a 0 vector, is equal to 5, which makes perfect sense. So 5 plus negative 7, it is 5, right? Based on this addition. What is our negative? Let's do negative b in this case. What is negative b going to be equal to? So if b is equal to 5, okay. Let's pick a different b. B is equal to 8. Let's suppose b is equal to 8, okay. What's negative b? Well, again, we can do negative b is equal to negative 1 times b. I used to right thing here, since we know it's a vector space. All right. Whoo. Now, gotta make sure I keep the right addition here and scalar multiplication. So -1 times v, -1 is the scalar, so I have, it's my c value. So I have -1 times 8, right, plus 7 times that -1 minus 1. I think that's right. Yeah, I think that's right. So I get -8 minus 14. That gives me -22. So the additive inverse of 8 is -22. We should check that out and see if that is really the case. -22. -22. I always have to check, especially when I'm like, I don't know, does that -22? That's a big number. Does that really work? Well, let's do v plus -v. We should get the 0 vector back, right? That's what we want to get. We want to get the 0 vector back. So v plus -v, so I get 8. Oh, sorry, yep, you guys got me. 8 plus -22. Okay. That's the same thing as 8 plus -22 plus 7. So I have 15 minus 22, and that's going to be -7. And -7 is indeed my 0 vector. So yeah. We found out the negative of 8, negative v's, the opposite, the number that we need to add to 8 to get my 0 vector is -22. All right, so that's pretty neat stuff.